Well, Pre-Calc Honor students, this is our last section of Chapter 6 on conic sections. Systems of second degree equations, where we're trying to figure out where the points are there on both two conics. Method 1 is an algebraic approach, like substitution or elimination, where you solve for y in terms of x, sub it into the other equation, or elimination, where maybe if you subtract the equations at just the right time, some of the variables will fall out. Method 2 is the graphing calculator, or GeoGebra. And then method 3 is a combination, which is probably what I prefer the most. A quick sketch can sometimes tell you that how many roots to expect, maybe no intersections. So here's our first example. xy equals 6 and x squared plus 4y squared equals 64. This is a good candidate for solving by substitution. And also, I'd like to see, before I get into all the algebra of it, is there even going to be a solution? This first one is kind of strange because it's basically a hyperbola, but it's not in our typical horizontal or vertical form. Y equals 6 over x is the way you can look at it, and it's a rational function with a vertical asymptote at x equals 0. And horizontal asymptote at y equals 0. Endpoints like 2, 3, and 3, 2, so we basically have something like this. And let's just put those in there so we get some idea of the reference. Now for this other one, we've got clearly a ellipse, because we have both x squared and y squared. Our x's and y's are squared. They're both pluses, but not the same coefficient. So we get x squared over 8 squared plus y squared over 16, which is 4 squared, equals 1. So the box of extent for this ellipse is 4 each way in the x, 4 each way in the y, and 8 each way in the x. So I think we're clearly going to get some intersections here, because we have to go through these points, and it's looking like 4 intersections. 1, 2, 3, 4. Just a really rough sketch to give us the idea that, yes, we are going to get some crossings. Now, in terms of actually solving, we can use what we've started already here. This y equals 6 over x. Combination isn't going to work too well if we add or subtract the two equations. Now the variables are going to fall out. But now we can put 6 over x in for y in this other equation to get x squared plus 4 times 6 over x, all quantities squared, equals 64. So that's x squared plus 4 times 36 over x squared equals 64. And we're going to need another page. Multiplying through by an LCD of x squared. And remember, we're using it to get rid of fractions in equations. So it becomes x to the 4th plus 4 times 36, 144, equals 64x squared, or x to the 4th minus 64x squared plus 144 equals 0. This really lends itself to a u substitution. If we let u equal x squared, then u squared equals x to the 4th. And you might find this a little more palatable here. U squared minus 64u plus 144 equals 0. I'm going to use completing the square because I got a nice even number here and the coefficient on u. So I'm thinking half of 64 is 32. 30 squared is 10 to the 4th. That's 1024. And we get u minus 32 quantity squared equals 1024 minus 144. And it gets again in a 0, 88, 880, 9, yeah, 880, which is not a perfect square. So that's okay. We get u minus 32 equals plus or minus the square root of 880, or u equals 32 plus or minus the square root of 880. Recall that that's x squared equals 32 plus or minus 880. We can get some perfect squares out of this somewhere. 4, not 100, but 4 times 220. And you can get another perfect square out of that with maybe another 4. Okay, here we are. I did make a mistake and I had to go back and redo everything. And so I've done all the calculations, and let's see, all because I put in 65 instead of 55. And that's one nice thing about making a sketch first. I went through this first, and I thought there were going to be 4 answers, just like our GeoGebra file seems to indicate here. But then when I was only getting 2, I realized I must have made a mistake. So I went back and I found it. And there we go, 4 answers. Now we go on to example 2, where you're given a pair of circles and the diagram this time, and we're trying to come up with where they intersect. So let's take a look here at all these, and let's see how well this is recorded over this. Okay, and here we go, 2 circles, and we're going to try and do it algebraically now. The 2 circles clearly indicate 2 points of intersection. Looks like 2, 4, and 4, 2. And here we're taking the first equation, x squared plus y squared equals 20, and subbing into it. No. What we're doing is subtracting the 2 equations from each other. Now I did that because I know when I expand this all out, we're going to end up with the x squareds and y squareds canceling out. So watch what happens here. X squared plus y squared minus x squared plus 10x minus 25 minus y squared plus 10y minus 25 equals 10. Cancel out the x squared negative x squared, y squared negative y squared, and we end up with this equation, 10x plus 10y minus 50, add 50, so you get equals 60, or x plus y equals 6. And that ends up being the equation of that line that passes through the points of intersection over there. And this is one of the theoretical ideas about when you combine 2 equations. The original intersections of A and B must make the 2 equations work and must make them true. And the only way we can subtract them from each other is if we know they're both equal. Well, they are both equal, but only at the points A and B. So anything that results from them, like x plus y equals 6, must also only be equal at the points A and B. And so that's why this line, x plus y equals 6, that results, has to go through those points of intersection. Okay, so now what we can do is take on this algebraically. We can look at the equation x plus y equals 6 and solve it for y as a function of x. So here we go. Y equals 6 minus x, and put that into the easier equation. So we end up with x squared plus 6 minus x quantity squared equals 20. So x squared minus 36x minus 36 minus 12x plus x squared equals 20, or 2x squared minus 12x plus 16 equals 0. And factor out 2, x squared minus 6x minus 8 equals 0. And so you get x minus 4 times x minus 2 equals 0. And there we go, x equals 4, or x equals 2. When x equals 4, we can go back into the y equals 6 minus x equation and come up with y equals 6 minus 4, y equals 2. And when x equals 2, you can go back into y equals 6 minus x equation. You get y equals 6 minus 2, y equals 4. So that gives us the 2 points, 2, 4, and 4, 2. There we go. All right. Now here's example 3, solving a system. 2x squared plus y squared equals 4, and x squared minus 2y squared equals 12. Well, this first thing is an ellipse, because we have both x squared and y squared. They're added, but they have different coefficients. So it's not going to be a circle. It's going to be the ellipse. X squared over 2 plus y squared over 4 equals 1. So x squared over the square root of 2 squared plus y squared over 2 squared equals 1. And now we can put up a picture of this. Just get a rough idea of the sketch here. And make the graph a little bigger. Okay. That's what we have here with our ellipse. X equals the square root of 2, so we go the square root of 2 in each direction. And that gives us basically the endpoints of the minor axis. We can go 2 each way in the y direction, giving us the vertices. Here's the box of extent, and the whole ellipse must stay inside that box of extent. There we go. Now, we might end up having to increase the size on this for more accuracy, but let's see what happens with the hyperbola here. Hyperbola, because we've got a difference in the squares, and it's going to be horizontal hyperbola because the x squared comes first in the subtraction. Get it equal to 1 so that we can see that x squared is over the square root of 12 squared, and y squared is over square root of 6 squared. So that'll give us the box of extent. And we can go square root of 12 in each direction. It's about 3.5. That's going to be our vertices. And go on the conjugate axis, go square root of 6, so that's about 2.5, 2.2, something like that. And notice we end up with a box of extent for the blue hyperbola, which entirely encompasses the box of extent for the ellipse. And so the ellipse is staying inside that box, and the hyperbola is going outside the blue box, so they can never meet. And we have no solution. Okay? No solution. No real solutions. And I think we'd end up with the same thing if we actually tried to do this algebraically. If we took the systems and maybe did some combination to combine these to solve them. So the algebraic approach would be to maybe take the top equation, multiply by 2, 4x squared plus 2y squared equals 8. And x squared minus 2y squared equals 12. Add them up. 5x squared equals 20. And here I paused for a while because I thought, oh, we're getting answers. Well, yeah, you do get real answers for x. But then, so 5x squared equals 20. 5x squared equals 20. So x squared equals 4. And x equals plus or minus 2. But then, when you put that back in, if x squared equals 4, you get twice 4 plus y squared equals 4. So that's y squared equals negative 4, and you get y equals plus or minus 2y. So you see you end up with imaginary coordinates for y. So I suppose if you were willing to have the y coordinates as complex numbers, you could set up a 3D graph of this and see where they're crossing in a real for x, complex for y space. Let me know how that goes. That would be worth triple pips. And sure enough, confirmed by GeoGebra that the ellipse and the hyperbola never meet. For our last example, we've got some inequalities. X squared plus 4y squared is less than or equal to 16, and x squared minus 2xy is greater than or equal to 0. So the first one's an ellipse. Both x and y are being squared. Unequal coefficients, so not circle, and they're being added, so it's an ellipse. X squared over 16 plus y squared over 4 equals 1. So we get x squared over 4 squared plus y squared over 2 squared equals 1. So we can go 4 each way in the x. Oops. 4 each way in the x. And 2 each way in the y. 4 each way in the x and 2 each way in the y. And that's our box of extent, and the ellipse has to stay inside there. There we go. There's the ellipse. And since it's less than or equal to 16, we can test a point like 0, 0. It works, so that means we shade the inside. The ellipse divides the plane into the interior and exterior regions. So we just have to test one point off the ellipse to see which way to shade. Now this other thing doesn't really fit any of the standard forms we talked about. It does fit the standard form for a general conic, but that xy term is probably going to twist it, and who knows when you might come up with a degenerate conic. So if we factor out the x times x minus 2y equals 0, we get x equals 0 or x equals 2y. And so that's y equals 1/2 x. So we end up with x equals 0, which is the y-axis itself. I'm making them solid lines because of the less than, greater than, or equal to. And y equals 1/2 x is a line with going through the origin with a slope of 1/2. So there's my other line. Y equals 1/2 x. Now, how you know which way to shade here is dividing the plane into 4 sections, and we should try a point in each section. I'm going to make a little chart here so you can see what's going on with each of these. Let's try first point in this section. Looks like 2, 3. 2, 3 gives you 4 plus 9. That ends up being, oh no, I'm looking at x squared minus 2xy. That ends up being negative, so that does not work. So that's a no. Now we can try negative 10, 0. Negative 10, 0 works fine. That's 100, so yes. So negative 10, 0 works, so that whole region is going to get shaded. So I shade this whole region. Notice the x-axis itself is not a dividing of the regions. Let's try 10, 0. 10, 0 also works. 10 squared minus 2 times 10 times 0 is 100. That's greater than 0, so yes, that works. So everything there gets shaded as well. I suspected that was going to alternate, but let's just make sure we'll try negative 2, negative 3. That ends up being 4 minus 12, so negative 8. Yeah, that's negative, so we want it to be greater than 0, so that doesn't work. So there you go. Now we can go back and actually shade in what we intend to be the solution, and that is all that stuff in that section that's inside the ellipse. And of course, the line itself. You could also go back and find out where those points of intersection are specifically to get a precise solution. And there's the GeoGebra answer. So there you have it. And thanks, Sean D. Sean showed me that you can actually enter in to GeoGebra an inequality, and it will shade it correctly. You don't have to go around and figure out the shading. I also saw that you can adjust how the shading's done. So I actually use stripes on this one, and you can change the width of the striping and the angle of the striping. So lots of nice tricks you can do on that. Okay, flange out.